Good evening, everybody. Last week, Madhav and others, they had gotten started on the Llama 3.1 model, and they talked about some basic things. But now, he said that he wanted a better explanation of this whole distributed training story. And I think that is an important part. While the vast majority of us are never going to probably have the opportunity to train a 405 billion parameter model, nevertheless, it is important to understand the fundamental principles behind how these models are trained at scale. Therefore, this principle of parallelism comes in, where when we increase the amount of compute that we have in order to train these models, what are the different techniques that we can use in order to increase the throughput? And increasing throughput is very important. That means you'll be able to use more tokens and train larger models on more amount of data in a shorter amount of time. Let's get into it. First thing is you need to take a look at is what is parallelism. You know that you have something called as you'll have multiple GPUs, right? You have multiple GPUs, and then you want to make sure that whatever model you're training, you're not going to keep GPUs idle, because the biggest crime that you can make when you have multiple GPUs and a huge amount of data in a large model is that the GPUs remain idle. So we want to make sure to utilize every bit of compute that all the GPUs have. Look at this particular story. You have a matrix X and you divide it into two parts, column wise, which is X1 and X2. Now, you can also shard it row wise, which is in X1 and X2. If you look at the matrix multiplication of X with A, and if you consider sharding the matrix X1 along the column and sharding A along the row axis, then the whole operation of X by A can be considered as two parts. You have the gray zones, which is on the left and on the top part for X and A respectively, and the red zones, which is on the right and bottom parts for matrices X and A respectively. So now what you could do is you can split these into two parts and have two independent matrix multiplications, one for the black part, one for the red part. Now the black part multiplied by the black part will end up in a 4 by 4 matrix, and then the red part with the red part will also end up in a 4 by 4 matrix. And then essentially the final matrix multiplication of X and A will be an addition of the black part matrix multiplication and the red part matrix multiplication. Now, why is this important? Because this kind of demonstrates that we can decompose matrix multiplications into smaller parts. And this is essentially the working principle behind what is known as tensor parallelism. So what you could typically do is, if you have a matrix X1 and you want to multiply it with a matrix A, then you could actually split the matrix A into two parts. And then what you do is essentially have X1 multiplied by one part, X1 multiplied by the other part, and then you would have two different components of your main matrix multiplication, and then all you do is just concatenate in order to get the final result. So that means what you could do is you could take X1, you could take A1, make a compute on one GPU. You could take X1 and A2, compute it on another GPU. These two GPUs would run in parallel, and then you could just recombine the results in order to get the final matrix multiplication. And why is this necessary? Because what would happen is, suppose your X1 times A1 is a very, very, very large matrix multiplication, and maybe your single GPU is not strong enough to do that. So therefore, it would make sense if instead of doing the entire matrix multiplication on a single GPU, you would divide your matrices into smaller parts, decompose them, do the individual matrix multiplications in parts, and then just combine them all together. Is that clear so far? I hope that main principle is clear. It's just the concept of decomposing matrices, splitting them over multiple GPUs, and then combining the results. That is what essentially tensor parallelism means, and this is the working principle. Somebody has any question? Oh, okay. People are saying okay, that's good. All right. So now, what I'd also like to do is, pardon this very, very messy figure, but I'm hoping that you can see how it works. So in our models, right, your transformer models, we have the MLP and the self-attention layer. We have two layers which are important. Now, the MLP has a upward projection and a downward projection matrix. So the upward projection essentially maps from a hidden size of x to 4x typically, and then goes from 4x down to x. Now, x to 4x and 4x to x might be very computationally expensive. Therefore, what we could do is we could have the original representation, the input tensor x, and you copy it two times. And then the matrix for up projection A would be divided into two parts, which is A1 and A2. So now X is copied into two parts. Let's say A1 is on one GPU, A2 is on another GPU. So X is copied to the first GPU as well as to the second GPU. Now the matrix multiplication of X and A1 takes place, X and A2 takes place independently. Then it is given an activation, and then there is a Y1 and Y2 activation. Similarly, Y1 and Y2 are multiplied with B1 and B2, which is a decomposition of the B matrix. Now, remember how we had done over here decomposition along the column and decomposition along the row? It is pretty much what is being done over here. The up projection matrix is decomposed along the column, the down projection matrix is decomposed along the row. And this essentially maintains the same semantics as the direct matrix multiplication of A followed by the B with the GELU activation in the middle. Now, with Y1 and B1 and Y2 and B2, you get the final activations. Now, what G does is essentially it combines Z1 and Z2, gives it through a dropout, and then you get the final activation, which is Z. So what happens is that instead of doing a very large matrix multiplication of X times A time followed by the activation GELU, followed by B, and then the dropout, you have divided the matrix multiplication into smaller parts, which are more decomposable parts. And then, because each GPU can now independently handle these decomposed matrix multiplications, all you need to do is just broadcast the activations and then reassemble the final activations. And that is called as simply as tensor parallelism. This is how you do it in the MLP. Then in the self-attention, there is a very similar thing. Essentially, what you do is you have the query key value matrices, right? You have the query key values. And then what you would do is exactly the same thing. You would have the original input activation over which you want to compute self-attention. You would have two copies, and you would have two splits of the query key value matrices. And these two splits will be done row-wise, of course. And then once you've done this, you do the standard, let's say, self-attention procedure for each of these individual splits on an individual GPU. You have the softmax, you have the dropout, standard self-attention architect, whatever you do. There's nothing special about it. You will have one piece of the activation Y1, one piece of the final activation Y2. Sorry, not activation. This is the final attention, the output of the attention, but before the final matrix multiplication. So that is Y1. You have Y2 individually on two different GPUs, and then you do the final matrix multiplication with the output matrix of the attention mechanism, which is B, and this B is divided row wise and not column wise. So just keep in mind the row wise and the column wise semantics, because essentially that allows you to visualize how you decompose a large matrix multiplication into smaller ones. Um, and then finally you have Y1 B1, Y2 B2, which leads to activation Z1 and Z2. You assemble them, which is done by G. You pass it through the dropout, and then you get the final output or the final activation as a result of the overall self-attention mechanism. So two very, very simple procedures. I would recommend that you go through the Hugging Face blog, which kind of explains this in very nice detail. And tensor parallelism is one of the ways people, as I said, reduce the complexity of your matrix multiplications by decomposing them into smaller parts using row and column wise splittings. Is this part clear as well? Any reaction would really help. Or if you have any questions, please ask. Yes, Apur, please go on.
So where is X being broadcast from?
So X. So what happens is that the X will be. So here's the thing, right? There will be batches. Suppose you have two GPUs. So now first GPU will have its first batch, and what will have a batch, and the second GPU will have another batch. Now, what is happening is X is actually there are two different batches. One batch is given to GPU one batch is given to GPU two. So actually, broadcasting is not just done from GPU A to GPU B, but now this whole batch is broadcasted among multiple GPUs. So technically speaking, there is an aspect of data parallelism over here as well, which is not very evident, but it is something to note that X is not present from one central GPU, which is then given to two different GPUs. It is essentially two data streams that are coming to two different GPUs. Then each of these data streams activations are broadcast to the other GPUs to compute halves of the matrices. Once everything is computed, these activations are rebroadcasted to the individual GPUs, which had the data stream.
Got it.
I
So
hope that
basically,
makes sense.
let's say a batch size of 16 was being there.
Yes.
And so GPU 1 will get batch size 8 and the GPU 2 will
You
get
could
the,
you could say that. You could say that.
and then there is like an all gather.
Yes, yes, you could say that. Alternatively, I mean, essentially, a batch size of k will be given to each GPU, and now that you're having two GPUs, you can essentially double the throughput because you can use the two GPUs not just for sharding the computation, but you can also use it to double the throughput by having additional data flowing in. There was another question. What was the question? How do we decide between column and row wise sharding? So you have to work the maths for that. This is very nicely explained. So when Maddie will share the slides, right? If you just go through the equations, it will make a lot more sense. And you have to do this by hand. And it's already kind of explained over here how row wise and column wise sharding is done. So I would say just work this by maths and go through the Hugging Face blog. It will give you more clarity. So in the lack of time, I can't keep on doing it again and go in depth. But the principles are essentially, you know, that a large matrix multiplication can be decomposed into smaller matrix multiplications. And then if you know the way if you understand how the individual tensor operations are done or the pointers operations are done, you'll understand how the row and column wise sharding is done. Right now, we have sharded it in two parts, but we can actually shard it into k parts and leverage k GPUs. Okay, so moving on, you know, this is called as tensor parallelism, which means you break down a large matrix multiplication into smaller ones. But then there is this concept of data parallelism, right? What data parallelism means that instead of if you have k GPUs, essentially what you could do is you can now parallelly process k batches at the same time. And what that means is if one GPU could handle a batch size of two, with k GPUs, you can have essentially handle a batch size of 2k. You've increased the amount of tokens that you can see per step by k times. And to put it in a very, very, very simple perspective, if you have a very small model and each model can fit on, if that model can fit on a single GPU, then you have the same copy of the same model on every single GPU. So GPU 1, 2, 3, 4 would have the same exact copy of the model. Then you would have your large batch or your entire data stream. You divide it into four batches, and each of these four batches would fit just exactly on that GPU without going out of memory. Now, each GPU processes that batch individually, parallelly, and then what happens is all of these GPUs, they have to synchronize their gradients. So they will all exchange their gradient information with each other, and then once the gradient information has been exchanged, each GPU has the same exact gradient information, and then the optimizer step takes place in order to perform the parameter update. There are different ways it can be done in practice, but the simplest way is essentially pass individual data streams to individual GPUs. Let each GPU compute the forward and backward propagation. Then every GPU should exchange this backward propagation information and then update the individual local parameters, because now every GPU has the correct exact gradients. And this is essentially data parallel. There's nothing magical about this. And as I had mentioned before, if you do tensor parallelism over here, essentially what you could do is you could take a model and you could break it down into two segments. So it could be spread over GPU1 and GPU2, and then the same copy of the model would be spread over GPU3 and GPU4. So now you could have GPU1, GPU2 representing one copy of the model, GPU3, GPU4 representing another copy of the model, but all of these will have the data streams. So GPU1, GPU2 will have to synchronize among each other to ensure that the activations and forward propagations and backward propagations are correct. But then all of these will have to sync, like GPU1, GPU2 as a group will have to sync with GPU3, GPU4 as a group and exchange the gradients to make sure that both these groups have the same exact gradient so that the updates can be done properly. So you can think of it as rather than each GPU supporting one model, you can combine GPU1, GPU2 to be a single super GPU, and now you have a data parallelism inside it as well. Any question? Okay, so to use the, oh, there have been many questions. Okay, you can decide based on the input and operation. That's correct. What if all the parameters of the model doesn't fit on a single GPU? Yeah, so essentially yes. If the parameters, as Vikas says, you can do FSDP, which is model parallelism, and then you can do offloading, as Vikas is mentioning. That's absolutely correct. Okay, so now data parallelism is done. So once you have data parallelism, you have to think about the actual big picture on how fully sharded data parallelism takes place. So what fully sharded data parallelism does is it takes an entire model and then divides it into k parts, ensuring that each k part is placed on a different GPU. Sometimes, so think about it like this, right? Suppose you have four layers in the model and four GPUs. Now, all four layers cannot fit on one GPU. So you'd put layer 1 on GPU 1, layer 2 on GPU 2, and so on and so forth. And then what would happen is that the data would be fed to GPU 1, which will do its own layer computation, which then that activation will be forwarded to GPU 2, GPU 3, and GPU 4, and so on. Then backpropagation is done. And once backpropagation is done, the gradients are computed, and then individual layer information will be updated on each GPU. But in practice, this means that once GPU 1 has done its job, till GPU 1 does its job, GPU 2, 3, 4 will be waiting. Similarly, during backpropagation, once GPU 4 has done its job of updating the gradient of computing the gradients, then GPU 1 still has to wait for GPU 2 and GPU 3 to finish its work. So in practice, this is not how it's done. Instead, there is a whole process of the data is stream is fed to each of GPU 1, 2, 3, and 4. There is a data parallelism aspect over here, where instead of giving the data directly to GPU 1 and then expecting it to go through this chain backward and forward, the data is given to each individual GPU. And then what happens is all these GPUs, they exchange the parameters of the different layers so that the model is assembled on each GPU on the fly. Then once the model is assembled on each GPU on the fly, a local computation is taken place, and then activations and gradients and whatever have been computed, they are constantly exchanged among multiple GPUs. And then once this exchange takes place, you can essentially process a larger volume of data, and there will be no stalling between the GPUs. Essentially, you do a lot of inter-GPU communication to assemble models, assemble gradients, and then ensure that there is a massive amount of throughput. And I've given you a very, very intuitive explanation because this is not the session for fully sharded data parallelism, but I hope the intuitiveness is clear. Essentially, we leverage a lot of primitives to exchange parameters across GPUs and exchange the gradients and underlying information among GPUs. What is the question? How will the parameter update happen across GPUs? So this is going to actually require an entire session on FSDP. I'm not sure, whether we have the time for that. But to give you a gist, PyTorch has primitives for broadcasting and scattering and gathering the different tensors which are present on different GPUs. And then FSDP ensures that the appropriate, let's say, primitives are used to send the appropriate gradient information. So if GPU 1 was responsible for layer 1, then FSDP ensures that whenever some gradient information for of layer 1 which has been scattered over to GPUs 2, 3, and 4, whenever that gradient information is present, that gradient information is rescattered back to GPU 1. So essentially what it is, FSDP internally takes care of all of this. And it's a very complex and elegant piece of code, but it really ensures that a huge amount of throughput takes place. So, Suresh, I'm not sure if I explained your question correctly, but intuitively just understand that the FSDP module uses a lot of PyTorch primitives in order to scatter and gather a lot of updates. Is that okay? Okay, cool. All right. So we have handled tensor parallelism, we have handled data parallelism, uh, and we've explained what FSDP is. Now, what you need to understand is pipeline parallelism. So now think about it this way, right? Suppose data parallel ranks 0 and data parallel rank 1. So essentially what it means is, think of this data parallel rank 0 as a single big mega GPU, and data parallel rank 1 is another mega GPU. So essentially the model copy between rank 0 and rank 1 is identical, and then each individual ranks are computing their own parallel information, their own parallel processing. And then what is happening is that at the final stage, both of these ranks exchange information among each other, which is essentially gradients, and then they update the parameters within each rank. So think of the upper part as one mega GPU, conceptual GPU, and the bottom part is another conceptual GPU. Now, if you look at each individual rank, think about it this way, right? If you have, let's say, two GPUs, GPU 1, GPU 2, and you have layer 1 on GPU 1, layer 2 on GPU 2. Now, if I gave you a batch of size 5, now if I gave a batch of size 5, it has to go to GPU 1 first. If it goes to GPU 1 first, then it would have to do an entire activation of GPU 1 for that model part which is on GPU 1. Then it jumps to GPU 2 and do the activation for that part. So essentially, till the entire batch has gone through every single network layer, now if a GPU was responsible for processing one specific layer, it is going to remain idle. And if it remains idle, which means we are just wasting compute, we are not using the compute capabilities of the GPU to its limits. So what people came up with is called as pipeline parallelism. Instead of processing one large batch in one go, they divide a batch into smaller parts. And then what they do is they give the first shard of the batch to the first GPU, which then lets it go forward. Once the first GPU has finished processing the first shard of the batch, the second shard is immediately given, and then the third shard and the fourth shard. And what eventually happens is that there is no bubble which is left behind. So if you look at pipeline parallelism rank 0, rank 1, rank 2, and rank 3, you have the different stages of forward and backward, right? So what it is doing is that first you're feeding the first shard, then you're feeding shard 0, then shard 1, 2, 3, and 4. And then once shard 0 has passed on from the first rank to the second rank, immediately shard 1 is passed on to the GPU. So we are preventing any bubbles from happening, and preventing any bubbles from happening, which means the GPU non-utilization remains to a minimum. Of course, at the end of the day, we will always have some amount of non-utilization taking place. But imagine if we had combined all the shards 0, 1, 2, 3, 4 into a single batch, then first it would, all the 0, 1, 2, 3, 4 would take into one single chunk. Then it would be given to rank 1, which would take another 5 blocks. Then it would take to rank 2 and rank 3. So then when rank 0 has finished processing, rank 0 would essentially not be doing anything useful. It would remain idle, and that would create a bubble in the compute. And we want to essentially avoid that. This is kind of also done in operating systems where you kind of interleave processes to make sure that none of the CPU is not spending time being idle. And that principle is essentially applied to pipeline parallelism to ensure that there are no breaks. To conceptually understand it at a very superficial level, what I would recommend is, instead of processing one large batch in one go, which has to jump from one rank to another or one GPU to another, break a batch or a shard into smaller shards so that each smaller shard has a smaller amount of compute time per GPU. And when one GPU has finished its processing, give that GPU the second shard so that it never remains idle. Any questions about that? And by the way, I'm trying to explain something rather complex in a very short amount of time, but I'm only giving you intuitions. I'm hoping that this will motivate you to go further and dig deep into this kind of stuff. Any questions? I hope not. Okay. And then finally, we are going to go into what is called as, not here, we are going to go into something that is context parallelism. Okay. We are going to go into what is called as context parallelism. And this figure actually is not doing a good job of explaining what context parallelism is. But to put it very simply, it means that we want to have large context, right? Now, everybody's training Llama with 8K context, with 16K context. There are certain models which have the ability to process 1 million context. So that means it means that this model has the ability to represent or process 1 million tokens or a sequence of 1 million tokens in one go. But we already know that if you do a 4096 cross 4096 matrix multiplication when doing self attention, that is already going to make you run out of memory in most cases. So how do these people actually manage to train models on long contexts of 8K or 128K or 1 million and so on? Well, what they use is called as context parallelism, and one form of that context parallelism is called as ring attention. So what they do is they divide the overall, let's say, sequence. So suppose you have a sequence of length 8, right? So they would divide the sequence of length 8 into two chunks, one sequence of length 4, the other sequence of length 4. Now, each of these chunks are given to two different types of GPUs. And then what happens is when the self attention mechanism has to be computed, there is a local self attention mechanism that is computed where that chunk is attending to itself. Then each chunk is also broadcasted to the other GPU or to the other rank. And on that GPU, a cross attention between one half of the chunk and the other half of the chunk is takes place. Now, what happens is because of this broadcasting, each GPU is only responsible for handling small chunk attentions. And then once each individual sub chunk attention has been computed, then GPUs broadcast this information again. And then across multiple GPUs, we will have captured a larger context or a larger chunk of 8 tokens. And that is essentially the working principle behind ring attention. What you do is if you have k GPUs, you divide your overall sequence into k parts. Each part is has a local self attention component, and then each part is broadcasted to every other GPU, so that now each GPU has an individual chunk coming in from other places. The local attention is computed with respect to the current chunk against the other chunks coming from the other GPUs, and then each GPU will have assembled the overall information for every single chunk, which is then redistributed back to the GPU responsible for for that specific individual chunk. And that is called as ring attention in a nutshell, or context parallelism. There are again different implementations of how people have parallelism, but this is probably the best way. To put it simply, once again, you take a long chunk or a long sequence, you divide it into k parts, give each part to each GPU. Each GPU or each rank is responsible for that specific sub chunk. Now, every single rank or every single GPU exchanges chunks with each other. Now, each GPU only is responsible for handling attention with the sub chunks coming in. And then every GPU just assembles the attention information for the chunk that it is responsible for. And that ensures that you have the ability to represent an extremely long sequence by ensuring that your overall attention is broken down into smaller parts. If you look at it, well, theoretically, it is a bit different from the way tensor parallelism is done, but tensor parallelism divided matrix multiplications. Here, you are dividing sequences into chunks and handling everything parallelly. And that essentially are the four parts of the parallelism. So there is data parallelism, which essentially ensures that k batches are divided into parallel and handled parallelly. There is tensor parallelism, which means larger matrix multiplications are divided into smaller parts. There is context parallelism, which means large sequences are divided into smaller parts. And then pipeline parallelism, essentially ensuring that your batches are divided into smaller parts, so that there are no compute bubbles in the overall GPU ranks or the GPUs over which you have distributed your compute. And I've speed run through this a lot, but the whole idea is for you to understand this figure, that we have data which is being handled parallelly, tensor or matrix multiplications which are parallelly done, context which is being handled parallelly, and then the data chunks being divided and being handled parallelly, so that there is very little idling of GPUs. And this allows you to get a huge amount of throughput. Okay, so there is one question. Does each token still attend to every past token in the ring attention context parallelism? Yes, actually, this is how they ensure it. So what happens is that if you have, let's say, the first four tokens and the next four tokens, the next four tokens is given to, let's say, another rank or another GPU, then the GPU responsible for the next four tokens actually sends the information of these four tokens to the first GPU. Now the first GPU computes attention information against this. And then similarly, the first GPU's chunk is given to the second GPU, and the second GPU's information is computed via self-attention to the first chunk. And then all the tokens are able to attend to each other. Does that answer the question, Apur?
Yeah, thank you.
Okay, cool. And that's basically it. I'll now hand it over to Madhav. Please take over, Madhav.
Sir, really thank you for the session, sir, on your busy time.
No, no, no.
I'm
It's
really
okay. Yeah, I think this is the intuition is important,
Yes, sir.
and my main motivation today was not like to actually explain, but to kind of give you what is the underlying principle or the philosophy behind all of these parallelisms, to ensure that we are not kind of because hopefully someday all of you will be able to play with maybe 100 billion parameter models, and at that point of time having an intuitive understanding of how things work is nice. So I'm hoping that at least you've gotten 50% of the intuition that kind of motivates you to go and read these things later and then get a better understanding.
Yes, sir. Thank you very much, sir.
Yeah, welcome.
Okay, I'll start my side of the presentation. Give me a minute. Okay, give me a minute. Give me 1 second. Yeah. Oh, yeah. Yeah. Hope you could see my screen. So with this all completed, let's get back to LLMs training. So right now, like we focused on how the data is passed towards the models. Now let's get back to the key defining parts of LLM. So in the last session, what we have shown is like how to pre-train on a large corpus, and then how to do IFT and SFT. So IFT and SFT, you just make it into prompt and you just train it on over cross-entropy loss. But today's session will be focused on this thing, the third part of it, preference alignment towards human beings. So, as we are training on large corpus, if you're typing into an chat GPT or something, its main aim in the first place is like predict next token, what's the context is given. Although rags and rag is there to ensure the model is being correct, and it at any moment of time the model go rogue, like say like explicit words or something. So to make it some kind of like human feasible, like safe for work, they do this preference. I don't know. Yes. In this thing, like on parallelism, in this thing, what you have to do is like you have to manually lay down the work and you have to manually split it out. So manually split it out, it doesn't mean that you will always like say these set of words and these set of words. Just say that these chunks go here and these chunks go there. So kind of like manual plus automated work. Hope that answers. Yeah. So let's go into that. Before like the pioneer of this, which is known as RLHF, what you do is like you will make a reward model, you'll train on a reward model, and then you use scale divergence. I hope everybody knows scale divergence. So scale divergence is nothing but if you take cross entropy loss and also consider the entropy between its own distribution, that is known as scale divergence. I'll come up on that in the later slides. So this is how you do it. I took it from the OpenAI paper. So first, you just ask the labeler to label what and all prompts is like really good or bad, and then you just get the reward here. You just get the reward here, like what they say, which is good or bad, and then you just use it with that reward. You kind of like do proximal policy optimization. So this involves in like if you keep on going on with the reward, at one point of time what would happen is like the model would just be blatantly human friendly, something like if you take can I buy this house for an example, it will just give you good or good, better, uh, great, something really positive words. So that kind of thing doesn't sit around with the main purpose of LLM. So to ensure that the model is not deviating from the answers which is supposed to tell, they use KL divergence. So this is the objective. So the objective of this, like this could be like really scary expectation, but I'll come upon that. So objective of this will be the current reward what you're training, and then the beta being like an hyperparameter, and log of the reinforced policy over given completion over the prompt, and supervised fine-tuned model given y over x. I hope it's understood. Please don't consider about pre-training context. What they taught in OpenAI is like, why can't I do this while I'm pre-training it? So that's why the gamma parameter comes in. But for real practical applications, as far as 2024, we could just initialize gamma is equal to 0. So we kind of like left with this thing, the expectation of the reward with this log of RL divided by supervised fine tuning of given prompts. So I'll come upon how KL divergence comes it here, but are you guys understood until what I said? Okay, I'll take the silence as yes, I guess. So yeah, so this thing, if you rearrange the terms, and we all know that expectation of a distribution is its summation of its probability function and the value of it. So the expectation of this can be, if you just take this out and make it as a separate summation, you could eventually come upon with this formula. KL divergence will be like expectation of log of this thing, this quantity. So this is the objective of this thing. So what in direct preferential optimization, what they do is this reward model, you have to additionally train it, and while training it, like if you want to additionally train some other model than LLM, it's going to be absolutely costly. So it's going to be costly to train your own LLM too. So to reduce that, to eliminate the entire need for a reward model, what they did is, if you like rearrange these terms, so from the KL divergence, you are coming back to the same thing, this thing again. And the policy within reinforcement learning is RL, is denoted as pi here, and supervised fine-tuned model, which is known as reference here. So if you do this thing, so initially we need to maximize the gradient. If you take the minus b beta outside, you will eventually will be like maximizing the minus expectation, which is nothing but minimizing it. So if you change these terms, you don't have beta here, you have beta here. So so still, like if you rearrange this, now if you multiply and divide by z over here, you could eventually come upon with this representation. So this thing is known as partition function. So if we could estimate this partition function, we could figure out the entire thing without sorry uh, entire reward modeling process without using the reward model itself. So if people like gone back into older days, Boltzmann machine uses this partition function to evaluate the probability of a particular configuration with given input vectors. Or in restricted Boltzmann machine, as Mitesh Kapra also gave an incredible lecture on it. Uh, in restricted Boltzmann machine, you also do the same thing, but uh, you are not connecting within the nodes. So that is like really primitive Gen AI. So that's the pioneer of Gen AI that I could say, Hop Wheels to Boltzmann machine. So Boltzmann mission laid the foundation of Gen AI, if you ask me. So yeah. So with this thing, here comes a tricky part. To minimize, yes, thank you, sir. So with this thing, what you could do is, if you look into, I'm sorry, like the mouse cursor is messed up. So let's keep this thing. So with this thing, if you look into this, if you look into this expectation, this also comes to KL divergence. I think I will give you a written proof after this lecture. So so primarily, if you want to use KL divergence or something, KL divergence is primarily used to evaluate the distance between two distributions. So let's say a distribution, probability distribution A and a probability distribution B. It's primarily used to evaluate the distance between these two distributions, because you can't use Euclidean distance and you can't use any other distance to evaluate it. So to have a minimum configured or a minimum energy function on this setup, we should have the distance between these two vectors as 0. So that's what they said. So if the distance between these two vectors are 0, it means that they are identical distribution. So that's how you get the optimal policy for the prompt generation. Given the prompt is this thing, 1 by z, 1 by z of x, and the reference of it, and exponential of 1 by beta, the reward process. So again, what does this reference process do? So how could you generate this reference? So still you should have a reference data set. So the entire thing summed up is like, if you want to select one prompt over another prompt, you could use sigmoidal networks. So if you look into this thing, this particular thing, if you calculate the gradient of it, it will be this. So you'll be calculating the likelihood, and you'll be increasing the gradient descent, like you'll be going down, sorry, you'll be going up on the most winning prompt, that is YW, and for the most losing prompt or more least preferred prompt, you'll be decreasing the model weights. So that's how you do uh, reinforcement learning with human feedback in a nutshell, within a within our model. So if you like take the reference from other data, other models, like you just send in a prompts in a GPT 3.5. So if you're sending those prompts in GPT 3.5, you'll get an output, and you could just mention like, this is most preferred and this is not preferred. So you're kind of like modeling the distribution of by reference. So, or you could just use your own model on an iterative basis, like just like in Q learning. That's what in Llama 3 also done. Uh, if you kind of do that without technically initializing a reward model, we could do RLHF. So this I took from a really good lecture from CS25 transformers. So that is one thing. So do gradient descent on good stuff and the gradient descent on bad stuff. So if you manage to do that, then you are just doing RLHF. So from this, anybody has some doubts? I think, does anybody have some doubts until this? Because yeah, Llama 3.1 is tuned with the DPO. Yeah. Okay. So I think like we couldn't cover these things. Let's put it on in the next lecture. This thing. So you kind of like get a SFT model, do DPO training, and then you take the best of it, again generate K prompts, and from the reward model, you just train it. So more on that on the next lecture. Like it's time now. So last 10 minutes, I'll be completing this DPO totally. So on the DPO pipeline, what you do is you sample the YW prompt and YL prompt, let it be Y1 and Y2, from a model which has learned the reference policy or something like, let me say something really simple. Just go to OpenAI, put a prompt there, give me two responses for it. So that's going to be Y1 and Y2. So in that, you're going to label a particular response Y1 as saying this is a most preferred response than this. So on DPO, you will be training on this loss function. So for Y1, you just do the log likelihood, and for YW, you'll also be doing a log likelihood. So if someone if you really into the older parts of the deep network, uh, the deep learning, it's kind of like really similar to Boltzmann machines. So on Boltzmann machines, on one configuration, you kind of like clamp those input vectors and train it on hidden layers. And another configuration, you'll just train it on just the entire network. So you take the difference of it. That's going to be your gradient. So that's how you do it. That the process is kind of similar to that, but not exactly that. So the code of it. So what you do is take the PA log P props, which is log P props. Give me by reference. Okay, log this prompts and then by this. So that's what they have said here. And then you apply log sigmoid loss similar to this log sigmoid, and then you just for the rewards you just multiply with beta minus this thing, as we discussed before. So you may ask a really great question. So where does this expectation value goes on? This part and this part, where does it vanish? We just calculating this. So a little primer on probability and stats. If you look into, like, let's say on a really large system, the expectation of the distribution would be converging to the mean value of it. So what you would be eventually doing it, you will be computing the entire expectation of the batch by just taking the mean. That's it. So if you take the batches as independent samples and which is providing these conditional probability distribution, you could just take the mean of it and say it as an expectation of the distribution. I hope everybody understood that what I said. So I kind of like end the lecture here because if I want to go on further, it's going to take like a lot of time. The expectation is the result of. I don't get it. Uh, is that a question or a point you are trying to make? I'm sorry.
Yeah, I was just trying to make a point.
Okay, okay. So expectation is the result of the end of the training. Yeah. So you can't exactly say that because the cross entropy loss can also be modeled to an expectation. But I was talking about, sorry to say so, sorry. So I was talking about for per batch iteration. So that's how you take expectation. So what you said is also right. Yeah. So summary of DPO. So DPO summary is nothing but you could just align your model with human preference with using the Wadley preference dataset. That's it. That's it. So with that, these things, the only interesting find what we have got is like they surpassed, they have found better way to train than chinchilla scaling. I will come upon that on next lecture because obviously like there is no time for it now. So yeah, so we are barely scratching the surface. Uh, and then this is the meme about me on the server. So Yeah, sure, 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 sure. So are there any ways to combine explicit rewards with TPO? So I think you could just compute the reward here just to say like what it is. But if you look into this, if you to look into this, you're kind of like taking out the reward term from it, because just by preference, you could just say like this is preferred over this, and instead of sending a scalar input, we are just doing it with just preference of the prompts from the HRAM, from the, oh shoot, I'm stuttering. So, uh, you just instead of like taking rewards, scalar rewards as RLHF, you could also technically compute the reward using this function, but we won't be explicitly using it because we could just do gradient descent on good stuff and gradient descent on bad stuff. That's it. I hope it answers the question. So this thing. So in this situation, we couldn't see reward here, but it's involved hiddenly. But we don't need to actually use reward on DPO. But to visualize it, we could use it. Yeah. So basically, if we got up, yeah, like yeah, exactly. So if prompt one is like really good, the prompt ones, oh sorry, the y1 is really good and y2, we just say y1 is really good than y2. That is because why it's simplified until this, because while training on RLHF, what they did is like instead of like taking k, I think yeah. K ratings, like one being really bad and K being really good. For that, I think K is equal to 5, I guess. Yeah, K equal to 5. So while fine tuning on this, like let it be 5 or let it be 1. So on fine tuning on this, what they actually came upon with is just overfitting of the reward model. So what they did is instead of like taking n examples, they took KC2 examples. So KC2 eventually being, if I take a reward 1, reward 7, and then reward 4, I'm actually saying, indirectly saying, this is better than this. So on DPO, instead of making them as a numbers, just say this is better than this by just giving you the sigmoidal output of it. I hope that answers the question, the gaps between both things. Yeah, this thing. And the code shown where will be the reward returned by EPLRs used in function further. So yeah, on this thing, rewards like you kind of like look into it. There is no actually like involvement on rewards explicitly being used on functions, just to look into it, or some uh, outside of what to say, outside of DPA optimization, you could use it. But I don't personally think reward will be like playing an influence on this optimization strategy. I hope that answers the question. So do we have, okay, yeah, so this scale divergence, so since we are minimizing the objective, what we do is like yeah, like I just gave you like a really primer information about it. I hope you like go into the presentation as well as the papers. But answering Apurul's question, the KL divergence here vanishes while we are while we are enforcing a minimum norm, because to be minimum, what we have to do is like we have to make this term 0. This term becomes 0 when these two distributions are identical to each other. So if it's identical to each other, then you have this function here. Hope that answers your question. Yeah. Yeah. Okay, you're just giving me a thumbs up. Yeah, thank you. So yeah, so I'll end up this session with this meme here. So yeah, so this is me. These two things will be coming real soon. I'm just stuck with my college works as well as my uh, with my life. So these two things would come. I will assure you. So with that, thank you very much for everybody just listening into this presentation, and I thank Raj sir for making uh, like making parallelization to explain as easy as possible, because he worked on a lot of other models, so you'll be like really doing it you'll be really giving it well. So that's why Raj Sabri sir was taking this part of this lecture. So yeah, thank you everyone. Thank you. So if you have any doubts, you could ping me in Discord, or you could follow me on LinkedIn, or give a connect. And then with that, I'm signing off. Thank you.